Hello, my name is Ian Sierra, and this is the Lab 4 video report. The purpose of this lab is to observe Faraday's law by dropping a magnet through a roll of aluminum foil, which represents a current producing a magnetic field that exerts a force on the source of the external magnetic field. We want to compare observed data versus a computational model. The concepts that are used in this lab are Faraday's law, magnetic flux, magnetic force, the Biot-Savart law, Newton's third law, and Newton's second law. The formulas associated with these concepts are listed at the bottom portion of the screen. Now on to the experiment. I used my smartphone, a bar magnet, a roll of aluminum foil, and a ruler for this experiment. The ruler was used for just measuring the aluminum foil dimensions. A ferrous tube is not used because the bar magnet will be attracted to the tube. I used my smartphone to detect which side of the magnet was the North Pole, which is necessary so that the north side of the magnet could be placed downward as it moved through the tube. I leaned my smartphone against a pillow to record the experiment. I held the aluminum foil in one hand and the magnet in the other hand, with the North Pole facing down. When I dropped the magnet through the tube, it fell at a slower rate than without the tube due to the effects of the magnetic force being inside the tube. I dropped the magnet through the tube 5 times and calculated the average time between where it entered the roll and where it exited the roll. The average time was about 0.95 seconds, which could be due to the dimensions of the aluminum foil, where the foil thickness was less than 1 centimeter and the length being about 30 centimeters. Now onto the code. The physical constants for mu naught over 4 pi, resistivity, and acceleration due to gravity are defined. The geometry of the tube of aluminum foil is inputted, including the length, width, inner radius, and total radius. The mass of the magnet and the magnitude of magnetic dipole moment from lab 3 were inputted. A function is created to calculate the magnetic field of the bar magnet using the formula for the Biot-Savart law. Then another function is created which will calculate the magnetic flux using the formula shown in the code, and it includes variables like the ring radius, distance, and speed. A simulation loop is created which will generate the model of the falling magnet. The gravitational force is defined. The ring current is calculated by dividing the change in flux by the resistance, and the magnetic force on the ring is calculated by using the magnetic force formula defined at the beginning of the presentation. The net force is found by adding the magnetic force and the gravitational force. The magnet's velocity and position are calculated using Newton's second law, and a graph of velocity versus time is plotted to finish out the loop. When we run the code, a model illustrating the magnet falling through the tube of aluminum foil is shown, where the magnet is represented by the red and blue cylinders. Our graph modeling the velocity versus time is shown, where the velocity is constant for a certain amount of time, which is the period where the magnet is falling through the tube of aluminum foil. Also, the constant velocity means that the magnetic force is equal to the gravitational force during its time in the tube. The time the magnet spins in the tube is printed. Interpreting the model. The blue cylinder corresponds to the counterclockwise current, and the red cylinder corresponds to the clockwise current. We know this because when the North Pole is facing downward, the magnetic field of the loop will oppose the magnetic field of the magnet, which also points downward. A counterclockwise current indicates an upward magnetic field of the loop found by the right-hand rule. When the magnet is flipped around, the bottom current, which will be red, will be clockwise. The experiment fall time was 0.95 seconds. The model fall time with mu equal to 4.336 equals to 6.092 seconds, and the model fall time with mu equal to 1.7 equals 0.956 seconds. The mu value found in lab 3 produces a much larger time result in the model than what was observed. This could be due to an error in the calculation of the mu value in lab 3. A much smaller mu value matches the observed results of the lab, and a proper recalculation of mu can make the computational model more accurate. Now on to the conclusion. If the resistivity of the conductor was reduced as close as possible to zero, the magnet would fall even more slowly through the tube, since the lower the resistivity, the more it opposes gravity. If holes or slots were cut into the tube, the ring currents in the model would just be zero since they would not be able to flow completely up and down the tube. Thank you for watching.